Okay, in this video, we'll be talking about energy of radiation and relevant topics. So, the energy of radiation, essentially, radiation is quantized. That's all I'm gonna say. Um, so, going back to the formula that has been discussed in the previous video, so energy is equal to the Planck's constant h and the frequency or v. In the previous video, I used F, but again, either way, it's the same thing. Let me try to remember what the Planck's constant is. It's 6.626 times 10 raised to 13. I hope I'm right. Just kidding. I got this correct though. 6.626 times 10 raised to negative 34. So this is what I have to remember. And I believe the unit is in joules. Okay, yeah. So when you multiply, so joules times seconds, that's going to be joules over seconds. That is the unit for energy. Okay. What relationships can you derive from the formula? So energy itself is, say it's directly proportional to frequency, and both of them are inversely proportional to wavelength. It makes sense because, for example, in the side of the electromagnetic spectrum where gamma ray is, it's characterized for having a really high frequency and at the same time a really low wavelength. So knowing that frequency and wavelength are inversely proportional, what you just have to add to that knowledge is that frequency is directly proportional to energy. So compared to the lowest, to the one that has the lowest frequency in the electromagnetic spectrum, which is the radio wave, gamma rays have the highest energy because they have the highest frequencies. So that's it. ABCs of UV radiation. We have three types of ultraviolet radiation: UVA, UVB, UVC. So each one has, as you can see in this table, there is a specific range of wavelength, relative energy, and characteristics. So let's start first with UVA. By the way, UVA, UVB are the two common types that affect the skin. UVC isn't. I'll get to it now. UVC isn't an issue to us unless we make it one, partly through climate change. But essentially, it is the most dangerous kind of radiation out of everyone else. It has the highest relative energy, the lowest wavelength range, only 200 to 280. It's very dangerous, but it's completely also absorbed or filtered by the ozone and oxygen. So as long as there's an ozone that's working, that has a fair amount of concentration, we're not supposed to worry about UVC. But it's a risk still. I believe that Antarctica, which has the lowest stratosphere compared to the rest of the world, that's where the ozone layer's hole is located at least the major hole. And that's where, well, it is rampant or easier to get skin cancer from that place. So yeah, more on that later. UVA, the wavelength range is between 320 to 400. Relative energy is at its lowest, is the lowest among everyone else. So this reaches Earth's surface in greatest quantity, and it penetrates the farthest into the skin. So it may be debatable. I'll just say it later. So penetrates farthest into the skin because it is the least energetic. So these two ideas are related. UVB, on the other hand, has a wavelength range of between 280 to 320. So the relative energy is medium. It is mostly absorbed by the ozone, which is, well, the ozone is located in the stratosphere. It is, some parts of its concentration is also seen in the troposphere, but it's not good. It's not supposed to be there. I think it's a greenhouse gas in that case. I'm not sure. Don't quote me on that just yet. And yes, UVB damages the outermost layer of the skin, of the human skin. So it may be said that UVB is more dangerous because it has a higher relative energy, but then at the same time, most skin cancer cases are because of UVA. Why is that? UVB essentially is most absorbed by the ozone, so it's not really much of a problem to us. Although unlike UVC, which is completely absorbed by the ozone and oxygen, UVB is only mostly absorbed. So some of it is still able to cause the, let's say, rare amount of cases. That's because of UVB. So UVA is more dangerous because it's more popular, and at the same time, yeah, it causes more damage to the skin and underlying tissue since it penetrates deeper. And yeah, it's I'm not sure if this is also a valid reason, but well, you can't deny that this is also a characteristic of UVA, that it has the lowest energy among everyone else. So okay, UVA penetrates deeper, UVB until the epidermis. Personal exposure to UV radiation. This is the minimum risk right here. If you don't have enough UV radiation exposure, basically sunlight exposure, you'd eventually get vitamin D insufficiency, and that's associated with being depressed psychologically. And if you really have no exposure to sunlight, you would have a higher risk of developing skeletal disease. But if you get exposed too much, there's a good chance of getting skin cancers and or eye disease. Okay, I won't be able to demonstrate everything that you have to know in this part, but what I completely understand the most is this part. So as you can see, the one in green, the green dot, means unpaired electron. In other words, odd-numbered electron. So this is essentially a free radical. So two covalent electrons form one covalent bond, supposedly. But there are cases where you only have one electron, and so that's unpaired. So free radical. More on this later, because one free radical in particular, which is I believe atomic chlorine. This is different from Cl2. Cl2 is the molecule chlorine. Because again, I think I've already mentioned this in the previous topic. We have 7 diatomic elements. Hydrogen, chlorine, that's 2 of them. But yes, essentially those elements only exist if they have 2 of them. So you can't say HO. Well, okay, I take back what I said. Usually it's just H2O. As well as oxygen. Oxygen is also diatomic, CO2. But yes, essentially, the difference between Cl2 and just Cl is that for Cl, this is called atomic chlorine. This is found in CFCs, or chlorofluorocarbons, and it's capable of catalyzing the reaction that decreases the concentration of ozone in the stratosphere. More on that later. There's a dedicated topic for that. But yeah, that's essentially it. So oxygen reacts with an electron that causes it to have just, can't really explain this part comfortably. Okay, hydrogen peroxide plus oxygen, hydrogen peroxide plus an electron, that's okay. So the ozone layer, how ozone is produced, you have energy and 3 oxygen molecules. That way you produce 2 ozone molecules. So mostly, again, it is situated in the stratosphere. So the stratosphere is the layer in the atmosphere that has the maximum ozone concentration. So around 12,000 parts per billion, or ppb. And yes, it is not good for the ozone layer concentration to be present also in the troposphere, although realistically there is, but it's kept to a minimum. Because what I said earlier was ozone is a GFG. I guess it's not. It's actually an air pollutant in the troposphere. Okay. Okay. Lewis structures. Let's review this. Should we? Maybe not. Let's go back to UV. Yeah, UV and the ozone. Okay. So Lewis structures. I'll be making a video for that specifically, but essentially in this part, how ozone reacts with UV. So you have two oxygens, atomic oxygens. Actually, it's not easy to discuss it if I haven't. Okay, never mind. Let's just include Lewis structures in this video. So what you want to know is, well, we have 8 groups for nonmetals. That's what we're gonna focus on here, for this specific part. Disregard the region for for the metals, or I think it's called transition metals. But yeah, all of these are metals. Let's only focus on the non-metals, which are these guys. Also, I admit that these are metals as well. Just disregard this rectangle region. Okay. So group 1A, that's hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. So essentially they have 1 valence electron. So that means 1 dot. We have group 2A, beryllium, magnesium, calcium, strontium, barium, rhodium. They have 2 valence electrons. For the third group, 3A, we have boron, aluminum, gallium, indium, tellurium. I'm not sure if it's correct, if what I said is correct. But essentially they have 3 valence electrons. For group 4, carbon, silicon, germanium. I'm not sure what this is. I'm not sure about the difference between the two, but essentially this group has 4 valence electrons. This one, group 5, has 5 valence electrons, and then 6, 7, and then 8. This is different from the ionic charge. The ionic charge, so we have for I believe these are the noble gases. Noble gases or halogens? confirm. What group is the noble gases? Yeah, so these are the noble gases. They have a 0 ionic charge. The hydrogen group, we have +1, then the next one is +2, +3. Here in group 7, that's going to be -1 ionic charge. And then this group of oxygen is going to be -2 charge, and then -3 charge for the nitrogen group. For carbon, I remember in senior high school, this is +4/-4. It depends. And I cannot elaborate further on that part. So yes, let's review the octet rule. The octet rule is where basically an atom, except hydrogen, tends to form bonds until it's surrounded by 8 valence electrons. Sorry. And this electron is, this specific kind of electron called the valence, is what you refer to the electron coming from the outermost shells of atoms. So, yeah. Carbon has how many valence electrons? It's over here, so that's 4 valence electrons. And hydrogen, being in this part of the region of the periodic table, it has 1 valence electron. So the way I drew it here, it might look confusing, but let me redraw that. We have carbon, hydrogen, 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 hydrogen. Carbon again has 6, right? 6 valence electrons. So 1, 2, 3, 4, 5, 6. Hydrogen has 1, 2. For each hydrogen, there's just 1 valence electron. So 2 of these valence electrons, they could form a single bond. Okay. So what? So we have two valence electrons. So they're basically considered a lone pair, such as the one here. So let's take this example. So coming from being that, it becomes this. So again, oxygen has 6, right? 6 valence electrons. Hydrogen has 1. So 1 each. They form a single bond. And yeah, that's it. The ones that don't connect with the hydrogens, they become lone pairs. Oops. Okay. So again, hydrogen is an exemption from the octet rule. But even so, the valence electron count or capacity of hydrogen is just 1. Okay. I've already said this earlier. Okay, covalent bonds again. This is defined by the formation between 2 nonmetals. So coming from here, carbon has 6, right? So let's count that. 1, 2, 3, 4, 5, 6. These all belong to carbon. How about oxygen? Oxygen, wait a minute. Carbon only has 4, right? Okay. Carbon has 4 valence electrons. So just this 1, 2, 3, and 4. Oxygen has 6 valence electrons. So initially those are the ones that I encircled belong to oxygen. So once they merge, so that. So we have double bonds. What's left as lone pairs are the ones here. Okay, next. So this time you have a triple bond. So carbon has 4 valence electrons, right? 1, 2, 3, 4. And then for this part, 1, 2, 3, and then 4. 4 for each carbon, and then hydrogen has 1. When you connect, it may not, well, just think about how this could be turned into a bond. 1, 2, 3. So that's going to be a triple bond. And this is what you get. In that case, there are no lone pairs. Okay, so for an exercise, we want to draw hydrogen bromide. I think that's how you call it. Essentially, it's a covalent bond. Again, hydrogen has 1 valence electron only. Bromine, where do we find bromine in the periodic table? Here. So it has 7 valence electrons. So 2, 4, 6, 7. And then when you connect, you have one single bond. So this is it. That's the Lewis structure. How about for Br2? I think bromine is also one of the diatomic molecules. Yeah. Have no fear of ice cold beer. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Yeah, 7. Have no fear of ice cold beer. I think that's how you remember the diatomic molecules, if I recall correctly. But essentially, 7 valence electrons each. You just merge, make a single bond from this to this. Okay. Molecular shapes. Just look at the illustrations. I'm not going to elaborate further on this. Ozone resonance structure. So resonance structure, essentially, for the case of ozone, actual oxygen bonds have properties between that of a single bond and a double bond. So UVB can penetrate double bonds. UVA can penetrate single bonds. Again, with the highest energy, so that's UVB, it can penetrate double bonds. Okay. So visualizing how ozone reacts with ultraviolet. So again, oxygen has how many valence electrons? 6, right? So essentially, when 2 are together, this is how it looks like. But then upon exposure to ultraviolet photon, more specifically the kind that has wavelength less than 242 nanometers, which I am guessing is UVC. Again, it helps to look at the range. UVC is 242, right? It's within this range, which corresponds to UVC. Okay, so essentially it turns this into, well, 2 oxygen, 2 atomic oxygens. So it breaks the oxygen bond to form 2 oxygens. Atomic oxygens, to be precise. And okay, so we have ozone. This is O3. When exposed to, what is this? Less than 320, this might be UVB. Because the range for UVB, I believe, is 280 to 320 nanometers. So it breaks the ozone bond to form oxygen and atomic oxygen. So this is the oxygen molecule I'm referring to. This one is the atomic oxygen. Okay, Chapman cycle. In order to retain the concentration of ozone, it should undergo the Chapman cycle, or in other words, the regeneration of ozone. So this is how it works. So from oxygen, so when it is exposed to UV photons, like I said earlier in this demonstration, um, so it becomes two atomic oxygens, and new oxygen is fed into the cycle. So we have atomic oxygen and, well, the oxygen molecule. And through fast collision, we get ozone. And as the ozone becomes exposed to UV photons of wavelength less than or equal to 320 nanometers, in other words, UVB kind of radiation, as demonstrated here, so we get oxygen and the atomic oxygen. It's exactly the same result here. So essentially this one, so that's the cycle for itself for this part. The ozone, where did this come from? O3 plus atomic oxygen. So there, a slow collision happens and we get two carbon dioxide molecules. And yes, the end point here is that the O3 is removed from the cycle, and yes, as a consequence, ozone concentration is maintained. This is what happens in nature. But there are instances where the Chapman cycle is unable to maintain the concentration of ozone in the atmosphere, more popularly because of man-made activities. So by the creation of of an ozone hole. I'll be back. I will end this video now. Sorry.